All right, here's an example from Cengel. We're in chapter 5 in their book. We have the water going through a garden hose and into a bucket. And they're going to fill this 10-gallon bucket. I have to do a conversion factor for that. The inner diameter of the hose is 2 centimeters. I do not like centimeters. And it reduces to a 0.8 centimeter exit nozzle. And it takes like 50 seconds to fill up the water bucket. We want to find the volume and mass flow rate of the water through the hose and the average velocity at the nozzle exit. So here we go. We'll look. I'll draw my little thing. I'll draw it. There you go. Here's our hose. It puts on the lotion or it gets the hose. Oh my God. I decided to do science. So the lamb's right there. And I messed. While I was doing that, I messed up my drawing. Pretty drawing. Here you go. Still not very good. Anyway, what we're thinking is making a control volume, like right there. And so we have mass flow rate coming in there, and it's coming out here. And they told us the inside diameter of this DI was 2 centimeters, what most people would call 20 millimeters or 0.02 meters. And what they say this one was, this was right here. There's the D exit of 0.8 centimeters or just 8 meters or 8 millimeters. There you go. Just centimeters confuse me. I don't know why. It's always bothered me. There's also, I drew it on my page, so I'm going to draw it here. Here's our bucket. Here, gotta put a little handle on the bucket. And this is 10 gallons. A 10-gallon hat. And if you wanted to convert the bucket, go 10 gallons. And I found this in the back of the book. You too can use the yearbook to find things. And I think it's right here at the beginning. Boom. And if you want to go to volume, right here, you'll see somewhere, they go 1 gallon is equal to this many cubic meters, right? So that's where I got that from. So we're like, where did you get that from? That would be the answer to that question. The question, where'd you get that from? I got it from there. And that was cubic meters per gallon. So we end up with a small number, but we could deal with it. Cubic meters. Gotcha. All right. Now we could get our volume flow rate. This is going to be the volume divided by the change in time. We'll call it change in volume because it changed. It was 0 and then it became something. So that's a change, isn't it? And so that's 50 seconds. So 3.785 E minus 2 divided by 50 is going to give us a lovely 7.570 E minus 4. And these are cubic meters per second. These numbers are getting smaller. Now, we could look this up. Look up specific volume. Spec vol. Can I write that? I guess I just did. And for water. And I don't want to look it up because I have this memorized. It's close. It's approximation. You think they got the hose perfect? I don't know what to say. So we could find the mass flow rate by taking the volumetric flow rate and dividing it by the specific volume. And if you don't believe me, we could just use units to confirm, right? So these are cubic meters per second. and divided by 0.001 cubic meters per kilogram, and that cubic meter is going to jump, and that kilogram is going to jump up to the top. It's always good to check your units. 0.7570 kilograms per second. At least it's a number that we could get our head around instead of this e to the minus 4 stuff. And is that one of the things we want to know? We want to know the volume and mass flow rate. So we have the volume flow rate and the mass flow rate. Woohoo! Right there. See, that's what they asked for, volume and mass flow rates. Woohoo! Now we want to get the average velocity at the end of this thing, right? So all you need to do, well, go back to how do you find a flow rate? You take the average velocity and multiply by the area. So, but now we want to have the average velocity, so we take the flow rate and divide it by the area. And I didn't bother calculating the area. I just went ahead and put the calculation right in there. We got, here's our volumetric flow rate. Point. No, I don't know, it's not a point. What were you doing? I was thinking about what I'm going to have for dinner. I don't know. I was thinking about picking up a pizza, but I don't know if it's like 6 o'clock. I gotta drive home pretty soon. Maybe I'll call it in on the way. All right. So anyway, I'm gonna do it in meters. There you go. There's 8 millimeters right there, and that's squared. And so the V average is going to be 15.06 meters per second. So if you were to answer all of these things, we said m dot was equal to 0.757 kilograms per second. V dot was a paltry 7.57 E minus 4 cubic meters per second. But actually, you can figure out that a liter is 0.001, or the other way around. Anyway, what you end up getting, it's by 3. 5, 7, so you go liters per second. And I almost put a thing on top of second. I didn't mean to do that. And then lastly, you can get the average velocity is going to be equal to 15.1 meters per second. And that's pretty fast. Good enough. Sure.